All right, good morning, ladies and gentlemen. Today we are going to go over some parts of those related rates problems that were assigned yesterday. And I'm only going to go over the ones that were suggested. So they were 3B, 3C, and then way down here, 5A. All right, so those are the only three parts I'm going to cover. Obviously, I will also post solutions to the entirety of these problems. But let's go ahead and start with 3B. All right, so this is one of those rate in, rate out type problems. So the idea is there's oil sort of floating in from the pipeline. And with these problems, I just think of it in a very simple way. I think of, okay, there's going to be some rate in, and that rate in is affecting the size of this pile. Let's think of this as a pile of oil. I know that the oil is, in this case, in the shape of a cylinder, but just for any rate in, rate out problem, I just think of it as, okay, there's some rate in that's feeding the size of the pile, but then at the same time, there's a rate out that is affecting the size of the pile as well. And in this case, we'll think of it as a pile of oil. So let's say that this rate in, let's call it O of T. And that's given to us actually in the description of the problem. So oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. So the rate that the oil is going into this pile is 2,000 centimeters cubed per minute. Okay. And obviously that's causing the pile to increase in size. But then at the same time, finally, a recovery device arrives in part B, and oil is being removed now from this pile. We call this, that's the rate out, and they tell us that this is R of T. And R of T is equal to 400 radical T centimeters cubed per min. All right, so you notice that O of T is constant. It's just always 2,000 centimeters cubed per minute, whereas R of T is a function of time. All right, so anyway, the question goes on to say, find the time T when the oil slick reaches its maximum volume and justify your answer. All right, so I want you to think of this. If O of T, so the rate in which the oil is flowing in, is greater than R of T, well, what does that mean? And again, remember, this is quote unquote a pile of oil. If O of T, if the rate in is greater than the rate out, then the pile is increasing in size. In other words, the amount of oil is increasing. All right, on the other hand, if O of T is less than R of T, then the pile is decreasing in size. Okay, so we have an idea that we know when this pile will be increasing, we know when it will be decreasing. And so if we can just find the exact moment when O of T is equal to R of T, this is when the pile will neither be increasing nor decreasing in size. And at that point, we could have either, a maximum or a minimum, depending on like if it's increasing then decreasing or decreasing then increasing. But either way, we are going to seek out when is O of t exactly equal to R of t. This is when the pile is not changing in size. All right, and so that's basically what we're gonna do. We're gonna set up this equation. Set O of t 2000 equal to 400 radical t. And it's a matter of just solving this equation. And I believe you get t is equal to 25, yeah. And those units are minutes, yeah. Okay. That's part B. However, we're not finished yet because it does say to justify your answer. So we do have to justify that this is a maximum value. And if you think about it, the function pause for a moment. Okay, so for justification purposes, I'm going to define a new function, let's say T, big T of T, where big T represents total amount of oil in pile. At time T. And this is the total amount of oil in just cubic centimeters. All right, well, how do we really figure out at any time T what the total amount of oil is? And this is essentially the function that we're trying to maximize, right? And we've actually found the time where it should be a maximum. We just now have to go ahead and justify it. So I just kind of want to walk you through, well, how do we obtain this function? In order to get the total amount of oil at any time t, well, first of all, we need the initial amount of oil, but I think the way this works, there is no oil initially, but let's ignore that for just a moment. I'm just talking in generalities. And then what we would do is we would integrate the rate in from 0 to t. And at the same time, we'd integrate the rate out from 0 to t dt. And this difference here, this integral of the difference in rates represents the net change in pile size, let's say, from t equals 0 to t equals t. Okay, so once again, t of 0 was just 0 in our case, so we're going to ignore it. So our function that we're trying to maximize is just simply this integral. Okay, and the question is, well, in general, how do we find the maximum value of a function? Well, we identify its candidates by differentiating. So the derivative of this function, well, if I differentiate an integral, the fundamental theorem of calculus part 2 tells me that this is just going to be O of t minus R of t, right? And so that's actually essentially the function. What I would do then is take the derivative and set it equal to 0. And of course, that's equivalent to saying O of t is equal to, when is O of t equal to R of t? And that's exactly what we solved already, right? That tells us when the pile is not changing in size. So anyway, we've discovered that O of t is equal to R of t at t equals 25. The whole point is now to justify. And how do we justify? Well, we use the first derivative test. Our function is O of t minus R. Our derivative function is O of t minus R of t. This is really what the timeline looks like. Here's t. We start at 0, and we go off to whenever. We've identified a critical point at t equals 25. And so we know that big T prime is equal to 0 at t equals 25. Okay, so now anything in between 0 and 25, we need to determine, really, we're interested in positive or negative. Well, let's see. Let's just choose something simple. Let's say when t equals 1. Well, when t equals 1, let me explicitly write out O of t minus R of t. Remember, O of t was 2,000, and R of t was 400 radical t. So when t equals 1, you can see that this number is clearly positive, which means that the pile is increasing in size within this interval. And then let's choose a number between 25 and, let's, in theory, infinity. Let's say 100, t equals 100. Well, when t equals 100, this second part here becomes 4,000, and that obviously will make 2,000 minus 4,000, that's a negative number. And so the derivative is negative when t is greater than 25. So what that means is that since t prime of t changes from positive to negative at t equals 25 minutes, big T of t is at a maximum at this time. Okay. A lot of work. I think I went into maybe a little more detail than is required, but the point is, when you're solving this problem and you get this t equals 25, you can't just stop there. You do need to justify it by using the first derivative test. All right. Justify by using the first derivative test. All right. Or if it's a closed interval, of course, remember the candidates would be just the endpoints and the critical points. So, and you'd put them into a table of values. Another thing before I move on to part B or part C is please be sure to show the units with your answers, especially if the question is given units. You should most definitely include units in your answer. Okay, so part C says, by the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Write but do not evaluate an expression involving an integral that gives the volume of oil at the time found in part B. Actually, so this kind of goes to the expression that we were, okay. So basically we essentially want the amount of oil at any time t. All right, so I just want to point out that the assumption that I was making before, that t of 0 equals 0, is not 100% correct. We're told by the time the device actually starts working, so when the rate in and rate out are both in effect, there is 60,000 cubic centimeters of oil. So really this is this is 60,000 cubic centimeters. All right, and so T of T, so the total amount of oil at any time T would be found by taking 60,000 plus this integral. But what I do want you to notice is that when we take the derivative, that 60,000 does not come into play at all. So our previous answer is still perfectly fine. But going into part C, big T of T is going to be found by taking the amount of oil at time 0. And I'm going to define 0 just for your purposes. 0 represents the time when the removal device started. Because they're not really specific with us. They don't really tell us at what time that was. So I'm just going to say, all right, we started counting when that happened. Okay. So how much oil was there initially? So that's big T of 0. Now plus that integral from 0 to, let's just use the letter B in this case. Oh, no, we're going to use the letter T because that's what my function is defined as. And then again, it's just the difference in rate in minus rate out. And that is the integral expression they're looking for. Going back to earlier in the video, remember that integral from 0 to t of O of t minus R of t dt represents the net change in the pile size from t equals 0 to t equals t. And it does not, it tells you do not need to evaluate it, so we're done here. All right, so that's part C. The total amount of oil is equal to the initial amount of oil plus the change, the net change in the size of the pile. And remember, that size of the pile is just the difference in the rate in and the rate out at any particular, over some interval of time. Okay, hopefully that makes sense. If not, of course, SGI is available and I could maybe go into a more detailed explanation, but I think I sort of did explain this earlier in the video. So if you want, rewind to when we were about this part of the screen, because I was kind of explaining that expression earlier on. Okay, let's move on to 5A. This is a tricky problem. I mean, there's so much information initially given. So I do want to pay attention to all of this information because they're not just saying things to trick you or fool you. There is a reason for all of this information. So they said that the radius is modeled by a twice differentiable function. Okay, so that's important. It just means that we can find the second derivative of the radius function. We are given, I want you to notice, this is the derivative of the radius function. Okay, we're not given the radius function, we're given the derivative of the radius function. We're also told that the graph of R is concave down. So we have points of R prime, but we're told that the graph of R is concave down. And they also tell us that the radius of the balloon is 30 feet when t equals 5. Okay, this is all vital information for part A. even. All of this information will come into play in part A. All right, we want to figure out the radius of the balloon when time is 5.4. Okay, I can understand why this confused people because we don't have, in this table, we don't have time as 5.4 whatsoever, nor do we even have an idea of the radius function. All we have is the derivative of the radius function. Okay, so what do we know about R? Well, let's go back to this piece of information. We're told that the graph is concave down. So what I'd like to do is, if that's all the information I have, I'm going to use that information to draw a diagram. All right, so maybe this is what R of t looks like. All right, well, looking at the time period in the table between 0 and 12, notice that the derivative of R goes from 5.7 to 4 to 2 to 1.2 to 0.6 to 0.5. So basically, the derivative starts pretty positive, and then it approaches 0, right? So if I want to get a better sense for what R of t looks like on this interval, I know there are no negative derivatives in this time frame. And so there's actually not going to be the negative half of the curve. So now I know that the curve kind of looks like this. Right? I know that the curve of radius is concave down, and I know that the slopes go from 5.7 to 0.5. So I know that it starts increasing pretty quickly, and then it starts to kind of flatten out. All right, so here's 0, here's 12, this is time, and this is the radius at any particular time. All right, so we want to know the radius of the balloon when t equals 5.4. All right, and by the way, this is not going to be to scale. All right, but this is what we're interested in. When t is 5.4, what is the radius? Well, I don't have any information about that point, but I do have information about a nearby point, and that is when t equals 5, I know that the derivative is equal to 2. So let's draw that. And so t equals 5 is right around here. The derivative, of course, is referring to the slope at this particular point. This is the R of t function. But so we're told that when t equals 5, the derivative or the slope of the tangent line is equal to 2. All right, so I know the slope of that tangent line is 2. Let me use a different color pen. All right, so I know the slope of that tangent line is 2. What else do I know about this point? Well, this last bit of information says that the radius of the balloon is 30 when t equals 5. That's another way of saying on this curve, there exists the point 5, 30. Right? When t equals 5, the radius is 30. So you'll notice that for this tangent line, I have a point and I have a slope. And so I can use point slope form in order to find the equation of this tangent line. So I have 2 times x minus 5 is equal to y minus 30. 2x minus 10 plus 30 is equal to y. And 2x plus 20 is equal to y. So that's the equation of this tangent line, and that's actually going to be the linear approximation that we use for part A. So I'm going to call this actually L of x. That's my linear approximation. So the idea goes that, well, let's use the letter, okay, it's fine. I'm going to use x. I'm going to use t, sorry. So instead of x, I'm just using t. T, t, t. So the idea is that the radius at any time t can be approximated by using this linear approximation, the equation of the tangent line. And of course, this works best with points, values of t that are nearby my anchor point being t equals 5. So let's do this for 5.4. So r of 5.4, I want to go back and adjust this. So this point, the coordinates of this point that I wrote here, it wouldn't be r of t, right? Because in this case, t is 5.4. So that would be r of 5.4. And that's what we're searching for. And that's what I'm using my linear approximation for. So r of 5.4 is going to be approximately equal to L of 5.4. And L of 5.4 is just 2 times 5.4 plus 20, which is 30.8, I believe. And then we should include units. So this represents the radius of a balloon, and radius is being measured in feet. So 30.8 feet. So r of 5.4 is approximately 30.8 feet in this case. Okay, and those were the only problems that people requested that I go over. I will have SGI again today and every day. So if there was maybe a part that I didn't cover in this video that you'd like me to discuss, please let me know. But until then, have a great day, and I'll talk to you soon. Bye.